Welcome, I'm Professor Sever, and today we are going to look at applications of the derivative. In particular, we're going to review and discuss increasing and decreasing functions and the first derivative test. Definition. What does it mean for a function to be increasing on an interval? Well, we have the definition stated. A function is said to be increasing on an interval I if a less than b implies f of a is less than f of b for all a and b in the interval I. And what you see here is the inequality. If a is less than b, then f preserves the inequality if it's increasing. So if you took f of both sides, you would leave the inequality alone, only in the case that f was increasing. Conversely, a function is said to be decreasing on the interval I if a is less than b implies f of a is greater than f of b. Notice the inequality is now reversed. So if f is decreasing, that says that f of b would have to be smaller than f of a. Again, for all a and b in the interval I. So here's an example. What does this look like graphically? So we have three intervals. The first interval is here. The second interval is in the middle. The third interval is the rightmost interval. And we see f is decreasing. It's dropping on this first interval, constant on the middle interval, and increasing on the right-hand interval. Graphical representation. So a theorem. How do we determine if a function is increasing or decreasing on an interval, open interval? So a sufficient condition, it's not necessary, but a sufficient condition is that if f prime is positive, then on the interval, for all x in the interval, then f is increasing. Conversely, if the derivative f prime is negative, for every x in the interval, then the function is decreasing on the interval. So, in summary, a positive derivative implies the function is increasing. A negative derivative implies the function is decreasing. How do we prove this? Well, we would use the theorem that we've previously developed and discussed. We would use the mean value theorem as a classical way to prove this result. Let's look at an example. So how do we find the open intervals on which a function is increasing? So here we have a simple cubic function, x cubed minus x. And the question is, find the open intervals on which the function is increasing and or decreasing. Let's reflect. Let's try to use this theorem. So let's take the derivative. If we can find out the signs of the derivative, it will tell us where the function is increasing and or decreasing, provided the function is differentiable. So first, let's take the derivative. The derivative of x cubed is 3x squared. The derivative of x is 1, so therefore the derivative of x cubed minus x is 3x squared minus 1. Now we've already discussed critical points in a prior video, so how do we find the critical points? Let's review. We know that there are two conditions that could be satisfied. A, the derivative is 0, or B, the derivative is undefined. So in part A, we set the derivative 3x squared minus 1 equal to 0 and solve. Here I'm factoring out the 3. Many of us might just have moved the 1 over to the other side and divided by 3. Either way, you can solve this equation and get x equal minus square root 3 over 3 and x equal plus the positive square root 3 over 3. I'm doing it this way just as an illustration of the factoring to foreshadow what may happen in the next steps. Since we're considering the signs of the derivative, it's easy to analyze the signs of the derivative if the function were factored, because we know, for example, positive times positive is positive, positive times negative is negative, and negative times positive would be negative. But we'll go through this more formally in a moment. Now, since f is differentiable, we know there are no points at which the derivative is undefined. Why is it differentiable? F is a polynomial. It's differentiable everywhere. So there are no critical points of type B. Now, that just means we have points of horizontal tangency. That's what it means for the derivative to be 0. Thus, the only values at which f has a critical point occur at plus or minus square root 3 over 3. Example 1 continued. So ultimately, since we're considering the signs of the derivative, our primary technique will be to construct a sign chart. Now you've seen already the sign charts have come up several times in this Calculus 1 course in this series. So here's another instance in which we look at the sign chart of the first derivative. Later, we will investigate the sign chart of the second derivative to determine concavity and inflection points. Now we are only interested in the notions of increasing and decreasing functions. So I have the completed sign chart. At your leisure, you can plug in and determine these signs for yourself. Here, let's just do one. Here I could choose 0. Remember, the derivative was 3x squared minus 1. We would plug in 0 to the derivative. That would yield -1. Therefore, on this entire interval, the derivative is negative, and therefore the function is decreasing. Similarly, I could use values of 2 and -2 to determine that the derivative was positive. See, I'm plugging into the derivative. To determine that the derivative was positive on these two intervals, notice I'm plugging into the derivative. That's why I have this sign chart labeled. This shows this is the sign chart of the first derivative. Nonetheless, we see on this interval -infinity to -√3/3, the function's increasing. On the interval -√3/3 to √3/3, the function is decreasing. And we see on this rightmost interval from √3/3 to infinity, the function is increasing. And I have these results down here as a final answer. And for completeness, I've graphed the function x cubed minus x. And we can see the function on this interval, -infinity to -√3/3, the function is rising. It doesn't matter that here it's below the x-axis, it's still rising on this interval. And on this interior interval, it's decreasing, dropping over the entirety of this interval. And finally, on the rightmost interval, we see the function is rising again. Again, the fact that it's increasing is not a statement about where it's positive and where it's negative. Remember, this is the graph of the original function. This is a sign chart of the derivative. Increasing corresponds to positive on this interval. Decreasing corresponds to negative on this interval. And finally, this interval where it's increasing corresponds to a derivative being positive. So it's a famous theorem, Fermat's theorem, not Fermat's little theorem or Fermat's last theorem, but this theorem is attributable to Fermat, and this is one version that we will use, and it's depicted in the leftmost graph, namely figure 1. If f has a local extrema at a, and f is differentiable at a, then the derivative is 0. So this is a great result. This tells us, at least for horizontal tangency, that relative extrema occur at critical points of the horizontal tangency. And similarly, we could say this is a non-differentiable case. Clearly you have sharp corners, 3 sharp corners, but I'm illustrating a theorem that's not stated here, but the companion theorem is these are points of non-differentiability. So the larger result is if f has a relative extrema at a, then f has a critical point at a. This is very important. This tells us where to look for relative mins and relative maxes. We look at critical points. And what we would want to then do is to develop a mechanism by which we could test the critical points to determine if the function has or does not have a relative extrema at that value. The converse is not necessarily true. So notice the derivative, this is the classic cubic function. The derivative is 0 at 0. We see a horizontal tangent. But do we see a min or a max here? No. So the converse of this theorem is not true. You can have a critical point that is neither a min nor a max. In fact, we'll call this a saddle point of the function f. Thank you for watching an introduction to the first derivative test, part 1. In part 2, we will actually phrase the first derivative test and explore initial examples and investigate why the hypotheses are important for this theorem. I'm Professor Sever. Thank you for watching this video production.